So in the previous lecture, we discussed valence bond theory, and we tried to develop the picture for chemical bonding using symmetry and group theory. So now let us continue the discussion of chemical bonding and move on to molecular orbital theory, which is more generalized theory to explain the bonding picture, right? So let's start with lecture 37. So today we will be discussing some aspects of valence bond theory, and then we'll try to compare it with MO theory, and we'll see what are the differences, and then we'll move towards linear combination of atomic orbital approach, which is used in MO theory. Okay. Okay, so in case of VB valence bond theory, we had discussed that the electrons subside within the interacting atomic orbitals. Or within the interacting atoms, you can say, right? So also there is no a priori way to decide which pairs of atom will form or should be considered rather as bonded pair. And choices are made based on chemical knowledge. This is what we had seen earlier, and these are the two main points, right? Also, if you see, it retains most of the atomic orbital character in bonds, or we can say in hybrid orbitals, because hybrid orbitals are going to form bonds. And also, if we say that, how do we set up the Schrodinger equation in this? So setup of Schrodinger equation deals with, so let's say if we want to calculate the energy of different orbitals and all, so then you need to set up and solve the Schrodinger equation. And what you have to do is you have to set up the Schrodinger equation, which deals with mass and position of individual atoms. And then those atoms are actually considered as particles which constitute the molecule, right? Constituting the molecule. Okay, so now let us see what happens, what changes in MO theory. So MO theory, by contrast, we can say, so by contrast, in MO theory, we construct new wave functions that define unique orbitals for bonded system. So this is in contrast to valence bond, where there is no a priori way to decide which pair of atoms should be considered as bonded pair. Okay. Further, if you look at the details of MO theory, so nuclei of the molecule are treated as, so nuclei are treated as one polycentric nucleus. So all the nuclei taken together are treated as one polycentric nucleus. As if, so let's say if I have CH4 here, and then I have a nucleus here, nucleus here, nucleus here, nucleus here, nucleus here. So instead of this, I'll be considering it as a nucleus, something like this, which will have centers like this. Okay, so this is how the nuclei are treated as one polycentric. So this is one nucleus, but which has many different charge centers. So it's one polycentric nucleus embedded in the electron density that surrounds the entire molecule. So if these are the charged areas of a polycentric nucleus, then this is also embedded into a electron density that surrounds the entire molecule. So look at the bonding description, which is different from valence bond. So in case of valence bond, we had considered that a CH bond, there are two electrons, which is one shared from here, one shared from here, and then there is a bonding orbital which overlaps like this, right? And then in this wave function, there are two electrons which are staying, right? So this is 1s, and then this is sp3, and this is s, and then there is a overlap between proton and carbon orbital, and then there are one electron pair which is residing in this overlap bonding orbital, right? So this picture is totally different from what MO theory explains. So MO theory says that there is a molecular orbital which covers the entire thing, and then all the electron density is present surrounding this entire molecule, right? Okay, so now let's also look at what is the basic idea. So we can say that the electrons occupying these orbitals, we can say molecular orbitals, are delocalized over the entire molecule. MO theory also has the possibility of one or more of the molecular orbitals may have significantly larger values of wave functions only in the certain part of the molecule. What do I mean by that? So it says that although the electron density is delocalized over the entire molecule over here, but there are certain regions where the wave function has significantly larger values. That means the electron density is more stronger here. There is more probability of finding the electrons at certain places which are defined as bonds. Okay, so it does say that there is electron density more in certain pictures, but still it considers the delocalized picture overall, right? So I hope the differences between the MO theory and valence bond theory should be very, very clear, right? Okay. So we can say that such localization or localized bonding, we can say, does not come as a postulate in valence bond theory. So it does not say that there is a delocalization of electron density and there is localized electron density. It only tells you that valence bond theory only tells you that there is a bonding orbital which is formed by overlap of the hybrid orbital and one of the atoms, and the electron density is subsided between those two, right? But this picture is totally different. I hope the thing is very, very clear now. So now, before actually going to develop the MO diagram using different examples by help of symmetry and group theory, let us see that what is the role of symmetry, how symmetry can play a role in MO theory. So role of symmetry is, so imagine that the MO molecular orbital has the symmetry of the molecule. Why it has the symmetry of the molecule? Because it is spread around the complete entire molecule, right? So once we say that the molecular orbital has the same symmetry as the molecule, so we can immediately think of applying symmetry and group theory rules, right? So now we can say that there is a symmetry playing role in formation of molecular orbital, right? Okay, so now before again we go on discussing the MO theory and how to apply symmetry and group theory to develop it further, let us see something called as linear combination of atomic orbitals, which further leads to molecular orbitals, right? So it's the linear combination of all atomic orbitals which are taken. So unlike in valence bond theory where we were taking linear combination or symmetry adapted linear combination of only the central atom, right? For example, only carbon in CH4 was taken to form the hybrid orbitals. In this case, we are taking linear combination of all the atomic orbitals. This approach is called as LCAO, or linear combination of atomic orbitals. So now let us start discussing this. So each molecular orbital is written as linear combination of atomic orbitals. This is the basic start. Okay, so we will see that we can also start with, let's say if we are talking about carbon and hydrogen, so we can start with carbon orbitals and hydrogen orbitals independently, or we can also start with the hybrid orbitals of carbon and atomic orbitals taken together, because the atomic orbitals of carbon eventually would give rise to hybrid orbitals, and that will combine with the atomic orbitals of proton. We'll see how it goes. So let's first start of various atoms. So one difference is that we are not talking about only central atom. We are including all the atoms. Okay. So we can say for ith atomic orbital, we can write it as phi I, and kth molecular orbital can be written as psi k. Okay, this is the nomenclature which we'll be using. So if we now write psi k can be written as linear combination of atomic orbitals, so I can say that summation over all I c I k and phi I. Okay, I can say that. So where phi i's are the atomic orbitals and hence eigenfunctions of that particular atom, right? Atomic orbital. This is the free atom we are talking about. All right. Also, phi i's are so chosen such that they are all normalized. Otherwise, we'll have to normalize it and take. We'll see how when we solve it, it will be required that we will normalize it. That means that if you take the integration of phi I star phi I over the space d tau, this should be equal to 1. This is the normalization condition, right? So now to get the complete description of MO, what do we need? We need to find out these coefficients Cik and corresponding energies. Okay, so by using linear combination of atomic orbitals, MO, a particular form of wave equation called as secular equation is developed. In some books, you will see that this is also written as characteristic equation. Is developed in following ways. So let us try to develop secular equation which will be able to solve it for the energies of different molecular orbitals and the coefficients which are required for this linear combination. So let's start. So we all know that we can write H psi is equal to E psi. This is the Schrodinger wave equation. Then we can also say, so H is the Hamiltonian, E is the energy, psi is the state function for molecular orbital. Okay, this we have already discussed before, so let's not spend time on this. So we can now write it as like this. Also, we can take out psi common. Now if we can write K over here. Now substituting the value of psi K from the above equation here, which is the linear combination. So what we can write is, so we can write, putting psi K is equal to summation I Cik phi I in this equation. We get H minus E phi I, and Cik is outside summation I, right? So H is the operator which will act only on phi I, because this is the function and this is the constant, so Cik will come out of this operator. You can write it like this. H is the operator over here. Okay, and this thing is equal to 0. All right, so now this is for I atomic orbitals. So let us take for simplicity only 2 atomic orbitals so that we can see how to solve this equation. So I'll say for simplicity, let us take a case of 2 atomic orbitals. Okay, so in that case, our I will go from 1 to 2, right? So I will have 1 and 2. So what do I say? Then I can say that this is my C1K H minus E phi 1 plus C2K H minus E phi 2 equal to 0. So I have just expanded this equation for two atomic orbitals, right? If there are more than two, so you can accordingly expand it. Okay. Now, how do we solve this equation? So now we have the energies and the coefficients. How do we solve this? So now if we multiply this equation by phi 1 and integrate over all space. So when I say integrate over all space, I mean that integrate over the space within the boundary conditions of this atomic orbital. So beyond which it will cease to act as eigenfunction. So only integrate within the boundary conditions, not over all space. But in general, we just write d tau so that we don't have to define the limits here. Okay. So both sides by phi 1 and then integration. So what do we get? We'll get C1K integral, and we will have phi 1 H minus E phi 1 d tau. So this is integration over all space. Then we have plus C2K integration phi 1 H minus E phi 2 d tau equal to 0. All right. Okay, so let me go to next page. Okay, so what do we have? So let me write that equation again so that we don't get confused. Phi 1 H minus E phi 1 d tau C1K C2K integration phi 1 H minus E phi 2 d tau equal to 0. Now let us define. See, all these integrals you don't need to solve, because some of the integrals, by the rules of symmetry and group theory, you should be able to simplify, right? How do we simplify that? We know that phi 1 will form basis for certain thing, H will form basis for certain things. So those irreducible representations can come in here, and then we can take the direct products here. So we can simplify this equation, right? So I'm not going to do it right now, but when we are taking actual molecule, you should be able to do that. Okay. So let us define these integrals. So we have, so if we see here, there will be a term called phi 1 H phi 1, because H is going to operate, it's an operator. H is going to operate on phi 1 and phi 2. So we will have this integral phi 1 H phi 1 d tau, and we will call this as HII. Okay. So in this case, I is equal to 1, where both the indices are same. So this will be called as HII, and this is called as Coulomb integral. And basically what it tells you is, gives you the energy of, it gives you energy of the atomic orbital phi I, right? So if you want to estimate the energy of phi I, you have to develop this integral, and this will tell you the energy of phi I, and this is called as HII. All right. Now the second one, which will come from here, phi 1 H phi 2 integration d tau. This can be called as Hij, and this is called as resonance integral. So in this case, I is equal to 1 and J is equal to 2 in this particular case, right? So this is called as resonance integral, and what does it give you? It gives you energy of interaction. Energy of interaction between pairs of atomic orbitals that are interacting. In this case, it is phi 1 and phi 2, right? So these are two integrals. Then we also have phi 1 t tau, which is equal to 1. We know that, and this is a normalization condition. So we already started with normalized atomic orbitals. So that's why we can substitute this as equal to 1. So this is normalization condition. We also have phi 1, phi 2, d tau, and this is called as Sij, which is called as overlap integral. What is the extent of overlap? It tells you about extent of overlap of two atomic orbitals. Okay, in this case phi 1 and phi 2. So that is very, very easy, and now you can actually rewrite this equation, the above equation, by assuming these indices. So let us see that what we have got. We have C1k, and we can now write it as H11 minus E. So H11 corresponds to the complete integral which I said, plus C2k, and we have H12 minus E equals to 0, right? Now similarly, if we multiply the original equation by phi 2. So initially we multiplied by phi 1 and integrated over all space. Now what we are doing is we will multiply the original equation by phi 2 and integrate over all space. So maybe it's better if I can write down the previous equation number so that it is easier for you to understand. Let me go back to the previous page. So if I give this thing a name, then let's call this equation 1. So we have multiplied this equation by phi 1 and integrated over all space. So now next what we are going to do is we are going to multiply equation 1 by phi 2. So instead of original equation, I will write this is equation 1. Okay, so that it is not confusing. So if we do that, we'll get a similar equation, but now what we'll get is we'll get C1k, then we have H21 minus E. Wait, there is one more term over here. E into S12. S21 plus C2k, and this will be H22 minus E equals to 0. So now you have equation 2 and equation 3. Okay. Now trivial solution for this is for equation 2 and equation 3 is C1k equals to C2k equals to 0, and that will satisfy the whole thing. But we are not interested in putting all the coefficients equal to 0. That means there is no atomic orbital mixing, right? So that is the trivial solution which we are not going to take. Now let's see what is the non-trivial solution which will equate rest of the things as equal to 0. If you remember, Let's call it as A1x plus B1y equals to C1, and A2x plus B2y equals to C2. So you can convert this into matrix representation and write it as A1 B1 A2 B2 multiplied by XY, and write it as C1 C2, right? In this case, we can apply Cramer's rule. You must be remembering Cramer's rule from your class 11th, when the matrices and determinants were used, and you would have solved set of linear equations using Cramer's rule, right? So what did we do there? So we had x can be written as solution as determinant, where we will replace the first coefficients by C1, C2, and second will remain as such, divided by the determinant of A1 B1 A2 B2, right? So this is how you can solve this equation. And similarly for y, substitute C1 C2 at this column. So you have A1 A2 C1 C2, and at the bottom you have determinant A1 A2 B1 B2. Okay, this should be clear. So applying the same Cramer's rule to this equation, what we have got, we will get H11 minus E, H12 minus E S12, H21 minus E S12, and H22 minus E. This determinant will go to 0. Now this is called as characteristic equation or secular equation or secular determinant. So characteristic secular equation or secular determinant. If you need to know more details of it, so you can go back and look at the quantum chemistry course, and there you will get it in more details. Okay, so now we can say that the values of HII, HIJ, and SIJ can be computed at some level of approximation, and thus one can solve. So again, you can see that you can apply symmetry and group theory or direct product, to be very precise, to be able to say which of these determine or which of these integrals will go to 0 and which not, and that will simplify your equation. So one can solve the secular equation for the values of E. Okay, so once you have got the values of E, let's see. So in this case, this is a 2 cross 2 matrix, so it will give you quadratic equation. If you have n atomic orbitals, so we will get n cross n determinant. N cross n determinant will give nth order polynomial equation in E. So you will get n values of E. That means you will get n different molecular orbitals when you combine n atomic orbitals, right? Because you will have n different energies. Some of them can be accidentally degenerate, some of them can be because of symmetry they will be degenerate, but you will get n different energies. So in this particular example, you have 2 cross 2 determinant, so you will get quadratic equation. So let's see what we will get here. If we solve the above determinant, we'll get 1 minus S12 square, and we get E square minus H11 plus H22 minus 2H12 S12 E plus H11 H22 minus H12 square equal to 0. Now this equation, all these integrals can be calculated because you know the atomic orbital wave functions. So you can set up the integrations, simplify some of them by direct product, some of them will go to 0. Those which will not go to 0, put them here, solve them, and then you will get the values of energy. So you will get two values of energy, right? So you will get roots will be E1, let's say, and E2, right? These will be roots of the circular equation, right? Further, this will give you C1K. If you substitute these values into the original equation, that was equation 1, you will get the values of C1K and C2K, right? So the coefficients will also be obtained. Once you have got the coefficients and the energies, so you have developed yourself the picture for the molecular orbital, right? So I think this is all for today. So in the next class, we will take up examples and see how actually using all these arguments which we have discussed today, how actually do we develop the molecular orbital diagram for a given molecule. Thank you very much.